slideshow will show you how the energy, solar energy, reaches our planet and how it is distributed and how it can be utilized at the end. The sun produces a large amount of energy, with intensity of solar radiation being about 63.3 megawatt per square meter on its surface. Since the sun rays spread out into the space, radiation becomes less intense as it reaches the edge of the Earth's atmosphere. They are parallel to the direction of propagation of the Earth's elliptical orbit. The intensity of the solar radiation falling on Earth's atmosphere changes. Therefore, a yearly average value is thus taken in the equal to 1367 watt per square meter. The solar radiation intensity falling on an outer surface of the atmosphere is called irradiance and is measured in watt per square meter, or the solar constant can be used as to calculate the irradiance incident on the surface perpendicular to the sun rays outside the Earth's atmosphere on any day of the year. Extraterrestrial irradiance on a plane perpendicular to the sun rays is given by following equation. The I0 being the intensity outside the atmosphere. ISC is the constant, solar constant, which is 1367 watt per square meter, and is the day of year. Right. Consider plane A, a horizontal plane at the point P on the Earth's surface. Then let us consider plane B, a surface parallel to the plane A, but on the edge of the Earth's atmosphere horizontal to the plane. Then let us consider the plane C, a surface perpendicular to the. Not all the points on the Earth's surface are perpendicular to the sun rays, but the value of I0 is the same no matter which point you consider on the Earth's surface. A useful quantity to calculate is the solar irradiance incident on the imaginary surface that is parallel to the horizontal plane on the Earth's surface. The irradiance on such a surface is smaller than I0 because of the cosine effect, and is the maximum amount of solar energy that could be collected on horizontal plane at the Earth's surface if the atmosphere did not scatter or absorb any radiation that is in cosine effect. I0 is the irradiance intensity of the normal plane. Irradiance intensity on the horizontal plane I0h can be calculated from the following equation, where theta z is the zenith angle of the sun described earlier, and I0 is the terrestrial irradiation intensity on its horizontal plane. It can be seen from the theta z is also the angle of incident of sun rays on horizontal plane. Since cosine values remains between 1 and -1, I0h will never be greater than I0. Radiation. The intensity of solar radiation is called irradiance and is measured in units of power per unit area, like watt per meter or kilowatt per square meter, megawatt per square meter, etc. But the total amount of solar radiation energy is called irradiation and is measured in units of energy per unit area, that is joule per square meter. Irradiation is given the symbol H, so that H0 is the total daily amount of extraterrestrial radiation on a plane perpendicular to the sun rays. H0H is the total daily amount of sun's radiation is continuous spectrum of electromagnetic waves. It is therefore good approximation of black body radiation. It has all the wavelengths in the range of 0.2 micrometer to 2.6 micrometer. This spectrum consists of ultraviolet rays in the range of 200 nanometer to 400 nanometer, visible light in the range of 390 nanometer, violet to 740 nanometer red, and infrared in the range of 700 nanometer to 2.6. Table 1 below shows the subdivision of ultraviolet range, and table 2 shows the distribution of extraterrestrial radiation of the solar energy. Atmosphere and the air mass. The air mass is defined as the ratio of the length of travel of that solar radiation into the atmosphere to reach a point on the earth, to the length vertically traveled into the atmosphere to reach that point of the earth is shown in the figure below. Therefore, outside the earth atmosphere, AM is 0 when the sun is directly over it, and AM will be 2 when theta z is 60 degree. AM is normally taken to be an average of 1.5. For a clear sunny day, this value is used for calibration of solar cells. Estimate of solar energy at the Earth's surface. The solar constant is the average extraterrestrial insolation at the edge of atmosphere. ISC equals 1367 watt per square meter. The Earth presents a disk of area A pi r square to the Sun. Therefore, the total amount of extraterrestrial insolation incident on the Earth is ISC into pi r square. This value is then divided by half the surface area of Earth, 4 pi r square by 2, which gives 684 watt per square meter. The average insolation incident on unit area of each facing the Sun. Further, this will reach due to the atmosphere. This is reduced due to the atmosphere. The solar panels are calibrated assuming that there is a power of 1000 watt per square meter. Rough estimate of a radiation incident on unit area H of the Earth's surface can be made if we assume that 30% of the sun energy is lost in the atmosphere and that the day is an average of 12 hours long at any location. H equals 0.7 into 684 into 12 equals 5.75 kilowatt hour per day per square meters. But practically, we assume that the sun is only at an appreciable strength for an average of 6 hours in the day, as is likely in more north latitudes. Therefore, H equals 0.7684 into 6 hours equals 2.88 kilowatt hour per day per square meter. This is reasonable figure, practical figure for calculation purpose. The above figure shows the yearly profile of mean solar radiation for different locations, Southeast Asian countries including India. The solid grey line shows the average value of the 5.7.5 kilowatt hour per day per square meter, and the dashed grey line shows 2.88 kilowatt hour per day per square meter. Area required to generate 1 kilowatt power on a rooftop, taking 2.8 kilowatt per day per square meter as reference, 17.5% conversion efficiency, and an average of 5 hours sufficient radiation, we can get 10 square meter area for 1 kilowatt power. This is equivalent to 100 square feet for each kilowatt power. This will be the basis for power plant design. There are two types of design approach. One for designing a grid-tied solar PV power plant, and the other is standalone solar power plant. Grid-tied power plants are possible because of the policies of government. A consumer can produce power and can also enter into power purchase agreement with local power company. There are two types of grid-tied consumer. One who produces extra power than is need. The extra power in the range of 1 megawatts, such producer has to sign a PPA, power purchase agreement, with the power company. Smaller consumer make power up to and exceeding 10% of their yearly consumption. This power will be paid by power company, but any power exceeding this limit will not be accounted. Grid-tied consumer facility thus can only be produced just 10% excess power only. The design can be based on the rooftop area available for every 100 square feet area. We can install 1 kilowatt capacity plant. For example, a consumer requires 300 units of energy per month. This energy can be generated in a 5-hour daily basis sunlight availability. Thus, solar panel rating will be 300 kilowatt hour divided by 30 days, that is 10 kilowatt hour per day. Kilowatt rating will be 10 kilowatt hour divided by 5 hours, because only 5 hours sunlight will be available. Thus 2 kilowatt will be the rating of the plant, and 250 watt 12 volt DC panels are available. So 8 250 watt panels will be required to make 2 kilowatt. Battery backup required will be 12 hours per day, 12 volt, 12 hours per day assuming operation. Backup will be generated 10 kilowatt hour every 12 hours. 835 amp hour, so 12 volt 835 amp hour battery will be required for a standalone solar plant. To increase the backup, multiply this AH number by number of days. For more than 1 day, backup require a battery with large DOD, depth of discharge. Diagram shows layout of the SVP power plant. Is self-explanatory. Those of you who have question, please give question so that we can reply on this. Right.